So,
Yeah. Finding the minimizer using the Hessian, it's not included. So yeah, because it I mean, for that, the problem is, you have to take the inverse. So the inverse, I mean, we haven't, I think, studied, right? So it's, if I'm not wrong, minus q
yes,
inverse c, right? Is it like
yes,
that?
I think.
So the problem is the inverse. So inverse matrix, I mean, in the inverse of a matrix, we haven't studied so far. So yeah, just forget about that. So we
Yeah,
keep
yeah,
this for the
I see some
next midterm.
formulas that we don't study. Yes.
Yeah, yeah. So in this case, yeah. So I would say the syllabus is a bit limited. So that also means that you can do good in the exam, inshallah. Uh, so okay, let's. Yeah, this is the chapter 1 and 2. So you have any questions specific to these points, or here you apply
Uh,
the formula, which is
uh-huh.
the quadratic formula.
Doctor, when we find the minimizer, it rely on drawing the visible set, right?
Yes, exactly. I mean, because the feasible set, I mean, tells you what exactly is going on, right? So once you draw the feasible set, then you can get to the minimizer. Like here.
So
So in this question,
if I made a mistake with the drawing, is it is there another way if make sure to is it my minimizer is right? Because there is a grades for minimizer and the visible set.
well, we can apply different tricks, right? But like in general, the minimizer should give you a minimum value. Okay, so let's apply the trick here. Okay, the trick says that this point, this is something like 0 and 1, right? And this point is 1 and 0. Okay, so because that the problem is, well, this is the function g of x. This is the line for g of x, and the others, they are the contours of the function. So either your minimizer would be here, or your minimizer would be here. So let's say, I mean, some student, he makes a mistake and he says no, let's say the minimizer is here. So this point is 1 0. If you plug it here, so 1 0, so what you will get, 1 minus 0,
One,
which will give you
one.
1, right? But the thing is, uh, just for an instant, I mean, try to see the other extreme. The other extreme is 0 1. So now we try to put 0 1, and as soon as you put 0 1, so which value you will get? 0 minus 1, you will get minus 1. So which one is smaller value? Because I mean, at the end of the day, we are finding the value of the function. So the value of the function, I mean, the smaller value is being found here, not at this point. So that means this cannot be the minimizer, because if you just simply plug this point in the function, well, you will get a higher value as compared to the value which you will get at this point. So this is kind of a trick to see that, I mean, because compared with this point and this point, obviously, this point is this point is giving us a smaller value. So that means this is the minimizer and not this is the minimizer. So this is kind of one trick. Like if you are stuck with 2 points. And you know, as you know that just like the boundary conditions, I mean, the most, you know, the problematic thing is really at the boundary. I mean, whatever is inside, whatever is interior, that's not really, you know, of much concern. Which is here or here, that's not, you know, making a big deal. The only problem is, you know, at the end points, at the extremes, right? This one and this one. And then, I mean, we know that because this minus x1, both of them will be less than equal to 0, right? And as soon as we multiply this with minus 1, so this will eventually, you know, become something like x1 is uh, strictly greater than 0, right? And same thing goes for x2. And this would mean that we would be only, you know, focusing on the first quadrant. We can't get to the second quadrant. We can't get to the third quadrant. And we can't even get to the fourth quadrant, right? Because both of them, they are greater than or equal to 0. So that means only, you know, our feasible set is the first quadrant. And here, obviously, I mean, we can go as much as possible to the right side, to infinity. And similarly, like the y-axis or the x2 axis, it can also increase as much as possible, right? Okay.
Yeah, right.
So this is, yeah, I mean, something which you can add, uh, right? And this could help you. This could help you really, because I mean, for this kind of a question, I mean, once you have got the right contours, you know, sometimes there is obviously, I mean, a tendency that we make a mistake and we go to this point. But if you go to this point, well, finding the minimum would be going to help you, because that would clarify that, I mean, if we compare this point and any other point, I mean, so any other point which would give, I mean, a smaller value, that means it's much better, because what we are looking for is the minimizer and the minimum, right? So the minimizer is the point which would give the minimum value of the function. Okay. So right. So what's next? Because, and I hope that it's clear here, you know, how to draw. So for example, as soon as you know that g of x will be equal to 0. So as soon as you put this equal to 0, so after that, you know, we just said that you have to express in terms of x2. So you just have to express in terms of x2. That means x2 equals to blah blah. So x2 should be on the left side. Whatever is left over, that is pushed on the other side. So we know that, I mean, this will be x2 equals to minus x1 plus 1. So minus x2 equals to, if it is x2 equals to x1, then, you know, we'll get a line like this, right,
135
with
degree.
45-degree slope. Okay.
I think the opposite, Doctor, because it's minus.
No, no. Yeah, I mean, I'm saying if x2 equals to x1, but here,
Mhm.
since it's x2 equals to minus x1, so yes, you will get a line, you know, this. And
Doctor, for the linear.
you add a value, you will go here. Sorry?
Mhm. For the linear optimization, always the drawing is either to these two lines, whether it's 45 degree or 135 degree, right?
Uh, yes, you know, well, obviously, not always, because what, I mean, here we are making it a little, I would say, simplified, because we are saying that, you know, for example, we if we add a value, so it will go up. If we subtract a value, that it will go down. So that means, you know, we can add anything, we can subtract anything. But here we are like making it simple, and we are saying that the coefficient is 1, right? So the coefficient is 1 here. But obviously, if it is a different value, so we will not get, you can say, the line with 45-degree slope or the line with 135-degree slope, right? but we will get, I mean, a line with different slope. And but yeah, for the time being, I think we can just, because this, uh, obviously, I mean, if you are able to solve this, that means, you are quite familiar with how the linear equations, work. So I think that's exactly what is, required from all this discussion. But obviously, I mean, it can become more complex, right? But as we have seen, there are special purpose solvers which can be used, in the real life. Okay.
I see.
So yeah, in this case, yeah, this is because here again, you can make a mistake that, and we have seen, many a times that sometimes, rather than, coming with, for example, this line, I mean, you make a line like this, and then, obviously everything will be changed because your minimizer has to be on this line, like g of x is equal to 0, because this is a constraint, this must be satisfied in all cases. So that is, yes, this is very important that, you you look at the h of x, you look at g of x, and then work on the function, right? So yeah, this was it. And then, we have this, what we call as the standard form. And in the standard form, I mean, what we are doing is mainly, we are just like working on the linear part and, working on the quadratic part, right? So if you have some kind of, this kind of a function, so we can say that, if you open anything like this, right, so you will get one quadratic term, one linear term, and one constant. Same thing goes here, right? But the Q matrix, because it would be, so what would be Q here? And another name of Q is Hessian.
Q will be 2200, I think.
Yeah, exactly.
2002.
It would be 22002, right? And just in the last week, we also, we had, I think, a great discussion that if you have like x1, x2, so it is treated as a no x1, x2. There is only, I mean, you will x2 square. And what you have to do is you have to just make the coefficients double. Double means multiplication by 2. Okay. So multiplication by 2. And for the linear part, I mean, yeah, you would have the C. So C would be, telling you that what is the linear part, and it is, quite easy to see from that the linear part, once will be minus 2x1. That means the linear part will be minus 2, and from the other one it will be minus 6, because you will get minus 6x2, right? So this is how, I mean, you can get the standard form. And then, it's not part of the standard equation, but we can, obviously get the constant. And the constant is simply, the last term in this case, which we'll get from here and which we will get from here, which would be, so what would be the constant, I mean, we would be getting?
think 0.
No, once you open 10, yes, thank you.
When I open.
It would be 10, because yeah, exactly. Once you open, so the first one, once you open this, you will get x1 square minus 2ab, so minus 2x1 plus 1, and from here you will get x2 square minus 6x2 plus 9. So the constant is plus 9, and from here you will get plus 1. So eventually it would be 10. So that is how, I mean, just like you can consider any production environment, so if you are producing like something, so you get some things as a byproduct. So similar is the thing that once, for example, you simplify this function, so some terms, they are quadratic terms, so based on which we would populate the cube matrix. Some terms are linear terms, based on which we would populate the vector, the column vector C, right, because it's a linear part. And last but not the least is populate the constant, which is k. So we can just take aside the constants. Okay, so yeah, this is exactly what he's doing here. And for the other one, which is g of x, the idea is that you will just put it equal to 0, and once you put it equal to 0, after that it's kind of smooth sailing, because you will just write the coefficients. It is 1, and here it is -1. So we'll just write like this, and we will just say that I mean, either you say this is C transpose, or you write it as a column vector in one column, and that you write that you mention that this is C. And we have to also mention what is B. Well, obviously in this case B will be equal to 0, because this is what we call as a affine form, right? So in affine form we write ax equals to b, so the constants, they are just pushed to the other side of the equation. So for g of x we will have 0 for b, and for h of x, I mean, it will be just like the minus x2, and you will write it like less than equal to 0, and 3 will go to the other side, and it will become -3, exactly. And then what we have to do, I mean, it's very difficult to analyze, so
Multiply by -1.
yeah, perfect. We will multiply with -1, and we will change the sign. So it will become like x2 is greater than equal to 3, which is exactly what is happening here. Okay, this one. So the x2, this is greater than equal to 3. You can see that this all, the minimum value is 3, and then we go in this direction. And as you know, the minimizer is for the unconstrained case, you can see the minimizer should be here. But because of this g of x, because of this h of x, the minimizer is kind of shifted, right? The minimizer is shifted because the constraints g of x or h of x, whatsoever, they have to be satisfied in all cases, right? We can't get away without them, right? So I mean, we have to satisfy the constraints. So it's a must. And then the table filling or this active constraints, it's just like if you get I mean, for the h of x, if you plug in the value, and you are, so by the way, I mean, you can get only either negative value or less than 0. because these are the only two options. I mean, you cannot get a value greater than 0. So either you are getting a negative value or you are getting 0. If you are getting 0, so this is known as active or binding. And if it is negative, we call it non-active or inactive or non-binding, right? So the active, this is related with the, it is equal to, you can say, it's equal to binding. And inactive, this is the same as non-binding, right? And one thing more, this is also, what we say, that this is strictly feasible. So another name, we say that this is strictly feasible. Okay. And I mean, where is it written? So it's written here, this one, that the strictly feasible is when you are getting a value which is less than 0. Okay, just typing, right? And if, for example, there are, let's say, hundreds of constraints, and only one of them is active. So if only one of them is active, so it is enough to put the point on the boundary, to put the point on the boundary. Okay. And then obviously, I mean, for example, if I say that there are more constraints which are active, so what would happen? Well, the point would still be on the boundary. But sometimes, there is a change that it may be on the boundary, but if more constraints are active, then the point would move. I mean, it would be on the boundary, but it would move towards an edge and later on to a vertex. So it all depends like how many constraints are active. And when we say constraints, the number of constraints, so they are defined by this H1, H2, H3. Like in this example, there are only H1, H2, but in other examples, there may be three functions like H1, H2, H3, and so on. Okay. So this is, I mean, quite interesting because that helps us to determine whether a point is on the boundary or not. And even if it's on the boundary, whether it is on the first one, since both, since the active set is, okay, since the active set is null, okay, yeah, there was a slightly some issue with the signal strength. Anyways, so if the active set is null set, so we can say that, okay, the point is interior. But for the other case, like the second and the third, the active set is non-null. So here it's only, I mean, one constraint which is active, and here, well, two constraints are active. So what happens is that for both of these options, we can say for sure that the point is on the boundary. But what happens is that here the point is on an edge, and here the point is on a vertex, right? So this is how, the things they happen, and the things become very interesting here because, for example, if only one constraint is active, then the point would be on the face. So either here, 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 right? You can consider something like a football. So it's just, the outer surface. So it is on the boundary. I mean, because anything inside is, I mean, if you consider a football, then anything which is inside you can't see. That is, uh, that is the interior, right? So if one constraint is active, we are somewhere here. If two constraints are active, we'll go to the edge. We'll move to the edge. And if three constraints, if one constraint is active, so yeah, we are on the face, two for an edge, three for a vertex, right? This is exactly what, they are telling us. But the thing is, all of these options. I mean, if one constraint is active or two constraints are active, or I mean, even more constraints are active, so the point is considered on the boundary. But I mean, just by looking at it closely, we can, still figure out whether it's a face, whether it is an edge, or whether it is a vertex. Okay. And then, yes, this interesting discussion about infimum, that sometimes, finding the minimum is not feasible, or you can say there is no minimum or minimizer. There is no minimizer. If there is no minimizer, well, certainly there won't be any minimum. Uh, but what we can do is that in all these cases, infimum can help us, because here, we are talking about the bounds. So if the problem is somehow bounded below by some value, we will not hesitate, and we'll say this is the infimum. And if we have like some, you can say, more extreme cases, like either the problem is unbounded below, so we'll say, okay, still there are no issues, the infimum can be still found, can be still defined. And if the problem is infeasible, I told you to remember, it's just kind of a flip. That, I mean, we move from minus infinity to plus infinity. And for the maximizer or the supremum, there is just, the two things, uh, they will be switched, right?
دكتور,
Yeah.
if if I get a function in the exam, and how can I draw? Because the drawing is a bit problem.
uh, yeah, so I mean, by the way, I mean, are you referring to this
Linear
kind of a
or
problem?
no, like the problems in the samples you gave us.
Yes. Yeah. Okay. Okay. Yeah, that's a good point. And what I can do is, I think I can open maybe, these sample exams, because maybe it's a good idea. Other things you can find, right? So let's quickly go through these, and I hope it would be, I mean, a good experience, right? So let's do this change. Okay, let me share the file. So the first thing, I mean, if you are like trying to draw, I mean, the linear equation, right? So what you need to do, I told you that you have to express in terms of x2. So just like x2 equals to what? So if you are
The,
able to write in this format, then,
the,
it becomes easier.
if you are sharing, there is no content.
Yeah, no, it's still being
Uh-huh.
uploaded. So
Okay.
just a couple of seconds. Okay, so here we go. Yeah. So yeah, in this one, for example, let's see. Okay, this is the problem, right?
Yes.
So in this case, the first thing, which is asked here, is to find, the values. So since there are two dimensions, right? We can just check there are two dimensions. So just this all, it would be, 2. So 2, 2, and 2, right? The set of real numbers, and in the power we would have 2. Since there is only, single function, so p would be 1. Here q would be 1, but there are two inequalities, so m would be 2, right? Yeah, exactly. So then, yeah, the problem is, for example, let's look at how to draw. So you need to express in terms of x2. So here, what is there? If I put g of x is equal to 0, so, in terms of x2 means x2 has to be put on the other side, has to be moved on the other side. So eventually you will get x2 equals to x1 plus 1. So that means x2 is equal to x1 plus 1. So x2 is equal to x1 is this one, right? Plus 1 means this will move just, slightly
Up.
upward. Yeah, right? So that is, the g of x. For the h of x, here is the thing that uh, if you put minus x1 plus 1 is less than equal to 0, because h of x is always less than equal to 0. So this plus 1 will go to the other side. This plus 1 will go to the other side, and eventually you will get minus x1 less than equal to minus 1, and there is no other way except to multiply, uh, this inequality with minus 1, and at the end of the day you will get something like x1 is greater than equal to 1 and x2 is greater than equal to 1. So that means, if I look at, so this is the line, for x2 equals to x1 plus 1. But now we are saying that x1 must be equal to greater than equal to 1, right? So that means on the left side I can't get. And since the function g of x is what? It is x1 minus x2 plus 1. So I am saying that the minimum possible value of x1, the minimum possible value of x1 is 1, right? So if the minimum possible value of x1 is 1, so the value of x2, because it is x1 plus 1, so that means this will be 1 more than this. So that will start from 2, right? So this is the first thing. The second thing is, now, you have to draw and you have to talk about this one, which is f of x. So in this case, if you put any value, for example, we put like 1. If I put 1, then what would happen? Like x2 equals to uh, x1 will have to be moved on the other side, so it will be like minus x1 uh, plus 4, minus x1, or no, sorry, it will be like plus 6, right? Because 5 will move here and it will become plus 5, so 5 plus 1 will be 6. So our x2 equals to minus x1. So that means what we are looking for is the function in this way. So we would have, contours like this, right? So that means we would have, the contours like this. But what we are interested in is just, one small point, that our function value is increasing or decreasing. As I move here, the function value is increasing or decreasing. So it's very simple. Just, you know that, I put 1. So if I put 1, it was something like x2 equals to minus x1 plus 6. So plus 6 means I would be somewhere here, right? So if I put, for example, minus 1, so if you put minus 1, then x2 will be minus x1 and 5 will move here. It will be 5 minus 1, which means plus 4. So eventually I may be here, okay, or here. And then, it means that the function value is decreasing in this direction, right? And if the function value is decreasing in this direction, then what I'm looking for is this minimizer. This point is the minimizer, right?
Clear.
And once you know the minimizer, well, you just plug in here and you can get the minimum. Okay.
Okay.
This is exactly, written here. So we are trying to guide you because we are trying to like say that find, you have to draw the contour sets. So for the contour sets, you will draw these straight lines. Obviously, there is nothing like quadratic. There is nothing like, power 2. So that means we'll get straight lines. We'll just get straight lines. We won't get any circles at all, right? So that is why, I'm saying at the end of the day, by inspection. Now here again, let's try to see, if we make a mistake. If we make a mistake, so this point, is the minimizer. Okay, let's say we make a mistake and we are not sure, for example. So let's take this point. So if you take this point, let's say here the value is 2. X1 is 2, and if x1 is 2, well, x2 is x1 plus 1. So it would be obviously 3. Okay, so if you plug it here, so x1 plus x2 minus 5. So here, if you put this point, so it will be like 3 plus 2 minus 5, which will give you 0, right? But if you are here, so it is just like 2 plus 1 minus 5. So 2 plus 1, 3, and 3 minus 5 minus 2. So you are getting a smaller value at this point.
Yes.
So this is how, you can work towards the minimizer and the minimum. If you see, the last two parts, as soon as you draw the contours, then find the minimizer, find the minimum. Now there is one more thing here, that there are a lot of parts. Yes, if the overall marks are 6.5, so even if you are not able to find, let's say the minimizer, still if you are able to, for example, do 4 of the parts, that means most of the things would be done, right? Even if you do not, if you are, let's say, not able to find the minimizer, okay, only 1 marks will be deducted, but the most of the marks, they are exactly based on uh, like how you approach the problem, whether you are following, because we are here trying to guide you, right? We are trying to guide you because we are saying, okay, let's first find the standard form, okay, then draw the feasible set or mark or whatever, right? Then draw the contours. Only then we are asking that, okay, find the minimizer. But the trick which I mentioned, you can apply. Why not? So with this, at least you can be sure that how the minimizer would look like. Okay.
Yes, right. Doctor, if you go to page number 9,
Yes. Yeah.
here in the Hessian, it's just directly take the two the square from the function and apply it just like this, or
Yeah, yeah, exactly.
in all
So
function.
like this is 2 and this is 2. So the Hessian is 2, right?
Uh-huh.
And well, it all depends. It all depends that what you will get. Like here, if you open the term, so there will be one term which will be x1 x2, and it will be minus x1 x2. That is why we are putting -1. So it all depends on the function, right? So
Yeah,
how
but
will we?
I mean the first part, the two here. It's always
Yeah,
take the square, the power always taking the power.
yeah. In this case, yes. In this case, because what happens is that you will get x1 square, right, from here, and from here you will get x2 square. So the
Yes.
coefficient will be yeah, but okay, but let's make a change, and then we'll see it won't be something like that. So just imagine that it is not x1, it is 2x1, right?
Yes.
So if it is 2x1, now if you open, so you won't get 2 here, you will get,
Where?
I mean, so I made a change, here. Okay, so it is like 2x1 minus 4 whole square,
Yes.
right?
I will get four.
So 2x1 minus 4 whole square, right? So what you will get here in the Q matrix?
Four, I think.
No, not 4, but rather 8. You know why? Because once you open the square, so I mean there is nothing to worry. I mean it's very simple one. So just we open it, okay? So once you open it, what you will get? You will get 4x1 square, right? Okay, let's write plus 16 minus 16x1, right? So this is what you will get. Like the square of the first term is 4x1 square. The square of the second term is 16. And if we multiply the two terms with 2, well, we would get 16x1. And now you apply the formula. The formula says whatever is the coefficient, make it double. So you will get 8, right? You will get 8 here.
Uh-huh.
So, but the thing is, if it is just like x1 plus anything whole square, or x2 or x1 minus anything whole square, at the end of the day, you will get only x square, x1 square or x2 square, right? But you won't get any coefficient with that. So that is why take the his. But what I hope so that if I make a small change, then you won't get 2 always value.
Doctor,
Yes,
you mentioned in the last lecture that first partial derivative.
yes.
If you give us an example for that.
The first partial derivative, right?
Yes.
I mean, how to calculate, for example, or right? Okay, yeah, right. So, how to calculate it? Okay,
Yeah, I
so
mean,
let's apply it. Yeah.
how the question will be like, because
Uh, yeah. For example, it can be even from this question that I give you this function, and I ask you that what is the first partial derivative. So you have to calculate, right? So what you need to do, the first thing you have to do is, you just write delta f, right? And please do not combine everything. So it is because it is partial differentiation. So we have to differentiate it separately along each dimension. That means the first time along x1, then along x2, then along x3. So this is the main thing. This is, the main thing. And after that, we just, take the terms. So I will just circle the terms where there is x1. So there is x1 here, there is x1 here, there is x1 here. That means while differentiating with respect to x1, I would get three terms. So I will just differentiate, and that's it. So I would get something like 10 x1, right? Or not, right?
Yes.
I will get 10 10 x1. Yeah, right, great. And then from the other one, I will get minus x2, right? And for the third one, third part of the third term, I will get
Minus 6, plus
no, no,
3, plus.
plus 2x3, plus 2x3, because from here the 2 will come down and it will be multiplied by 5, so you will get 10x1 here. Well, the x2 you can just keep aside, and the derivative of x1 with respect to x1 will be 1, so you will get minus x2. Same thing here. I mean, from 2x1 x3, well, the constants which are like 2 and x3, you can just keep aside, and the derivative of x1 with respect to x1 will be 1, right?
Yeah, you're right.
And then, I mean, if I go for the derivative with respect to x2, what I will get?
Minus 6 multiplied by 2.
Yeah. So that will be
Minus
12,
12.
right?
Yes.
x2. And then what I will get?
Minus x1.
Minus x1, yes.
And
Okay.
plus 2x3.
Not plus 2x3, minus, while you are changing the sign, right? So here, it's minus x2, x3. So we can just take aside, for example, minus x3, and whatever would be left over is x1. Sorry, yeah, this is x2. So the derivative of x2 with respect to x2 will be 1. Okay.
Okay.
So now if we go for the third one, so it will be 4x3, right? 4x3. What would be the leftover part? Plus 2x1, right? And minus x2.
Minus x2. Doctor, we always take the coefficient of the x. Like here, when we are in x3, we take the x is close to x3 in the function, right?
Yeah, I mean, if it's like plus, so if it is plus, well, it would be plus. And if it is minus, then it would be minus. Because the thing is, if it is like minus x2, x3, okay, and I am taking the derivative with respect to x3. So what I can do is I can consider that minus x2 is taken aside, right? So minus x2 is taken aside, and then the derivative of x3 with respect to itself would be 1. So at the end of the day, I will get like minus x2, right? So in this one, the main thing is that, you have to do the partial differentiation. I mean, I cannot, in any case, combine all these three. They are separate things, right? They are in different cells.
Yes. And this is the final answer for differential.
Yeah, exactly. We can't like simplify it any further. So yes, this is the differentiation, exactly, the partial differentiation, right? And there are three rows, because you have to take the derivative with respect to all the variables, and there are three variables, x1, x2, x3. So that means, I mean, first time I have to differentiate with respect to x1, then with x2, then with x3. Okay. The second part we haven't covered so far. We would have a look later on. So this is also very interesting, because I mean, here it looks like it's in the standard form. It looks like it is in the perfect form. So there, but it is not in the standard form. Why? So why? What do you think? Why it is not in the standard form? Because the standard form we have already studied, right? Because there is no half, right? If you look at the standard form, in the beginning there is half. If there is no half, so it is not in the standard form. But what we can do? Okay, we go to the basics. So multiply x from the left, multiply x on the right, then just write it like the linear part as it is. Okay, just do it, and then you can find, you know, the quadratic part or the Hessian. You can find later on. How you can find? Let's say, I mean, you get this one. So if you get this one, what you need to do is just, you know, double the coefficient here, and x1, x2 is also quadratic, right? Similarly, x1, x2, since they are symmetric, so we can combine these two. So q12 plus q12, 21, they will be in the principal, sorry, the other diagonal. And the last but not the least is whatever we have here, we have to multiply with 2. So you'll get 2q22. Okay. So yet, I mean, this is another problem. And here, I mean, if you put g of x equals to 0, so x2 will be x1 plus 2. So x1 plus 2 means, if this is the origin, so this line will cut the other x's at 0.02. Okay, right? That's great. So, any other questions you have? So if you have any other questions, we will discuss that.
Doctor,
Yes.
for the direction of the steepest descent,
Yeah.
we take the minus delta f of x.
Exactly. Because the direction of the steepest descent, which is given by delta x, it is always opposite of the gradient. So you just calculate again the partial derivative or the gradient, and it will be just the opposite. So you have to multiply minus 1.
So I take the
You have to take the derivative.
yes.
The derivative. Yes. So the derivative, then the derivative at a point, and then you make it negative. That's it. So you take the derivative, right? This is the first step. You take the derivative, then you take the derivative at a point, and then you multiply with minus 1. So that's it. Okay.
Okay. Delta derivative of x, it's the same as find the gradient, right?
Yeah. The first derivative or the gradient or the slope, they are all, the names of the same concept. So these are similar, these are same things.
So the gradient is opposite of direction of the steepest descent.
Yes, yes, exactly, exactly. Gradient is opposite of the direction for sure. So they are like working in the opposite direction. Yes.
Okay. Doctor, here in this page for the drawing in the quadratic form.
Yes, exactly. So
Uh,
yeah, how we do that, right?
yes.
So in this case, the main thing is that the function. If you look at the function, uh, I mean, we know that there is something very peculiar, something very common, or what we have seen multiple times. So there is like square. So there is like something like x1 plus or minus whatever, some constant, and then there is square, then there is the same thing, and then there is this additional part, right? This additional part which would make it as elliptical. So we won't get like perfect circles, but we would get ellipticals like this one. Okay. So in this case, by the way, we make your life easier. So we just say c is equal to 0. If c is equal to 0, that means this part is gone. This part is nowhere. So after that, what you need to do is very simple. You just look at the value which is here, and if it is with a minus, so there is nothing to be done. So I can just take 5
It's like
and 3.
minus A minus B.
Exactly, because the formula says x1 minus a whole square, right, plus x2 minus b whole square, and this is equal to r square. So in the formula, everything is squared. So x1 minus a whole square plus x2 minus b whole square equals to r square. So if it is in this form, so here we can see exactly this is in this form, because the two terms, they are being subtracted. So then it's a good thing. Just we take 5 and 3, and that is our center of the circle, right? Okay. So this is like
Right.
the center of the circle.
So and then we take the values and take the square root of the values and
Exactly, exactly.
make
Because
the
the formula is like x1 minus a whole square plus x2 minus b whole square equals to r square. So the function value, it's equal to the radius. If we want to get to the actual radius, well, no problem, but we have to take the square root. Okay.
okay.
So this one, another example, that if you have like 9x1 square, 7x2 square, 3x3, so all these, they make the principal diagonal, right? They will make the principal diagonal, which is this one. And we have to make it double, but not the square. Just making double means multiplying by 2. So we'll get 18, 14, and 6. But if we look closely at the next 3 terms, so we know that these are also quadratic terms. So minus 2 x1 x2. So if you consider this first row for x1, then we have x2, then we have x3. So I mean, here with x1 x2 there is minus 2. So we'll write it here. We'll write it here because the Hessian must be symmetric, right?
Yes.
And then x1 x3, so we'll write 4 and 4 here, and minus 6 x2 x3, that means we'll put minus 6 here and here. And the constant, we can just write it separately, which is 6. But since there is no term, not a single term with only x1 or only x2 or only x3, So we can declare safely that the linear part is 0. There is no linear part at all in this question. Okay.
Okay. Doctor, one question. If you go to
Yes.
page number 9,
Yes. Okay. Yeah.
here in the gradient, the
Yes.
first derivative, we take we differentiate the x1 minus 4,
Yes.
and then we take x2. Why x2 not x1?
Yeah, because the idea is that we have to, by the way, take the derivative of all these terms. That means all the three terms with respect to x1. So first we take the derivative of this one. 2 will come down and the power will be reduced by 1. And then what we will do, we will take the derivative with respect to again x1, because whatever is in here, I mean, we have to take the derivative again. So here, by the way, this is x1. But just like I mentioned, if I make one change and I put it like 2x1, so that means you will write this as it is. But if it is, let's say, a small change and it is 2x1, so you will also write 2 here. You will multiply. You have to multiply, because this is, how the differentiation is defined. Okay. So anyways, so we get it like this, but the next term, there is no x1. So that means the derivative of this term with respect to x1 would be 0. And for the third term, I mean, what we do is, again, same thing. We take out the constant. So if and while, I mean, I am differentiating with becomes a constant if I am differentiating with respect to x1 and vice versa. So here, I mean, since I'm differentiating with respect to x1, so x2 minus 2 is treated as a constant. So it will be just taken aside. And the derivative of x1 minus 4 with respect to itself is just 1.
Mm-hmm. Okay.
Okay, so you want to ask any other question?
Yeah, the same question, Doctor.
Yes.
The absolute, the here, the square root of 4 plus 16. From where does it come?
Yeah, this one.
Yes.
Okay.
I mean, the
Yeah, this
same.
one, I think, I don't know whether we have taken, I think maybe we haven't taken it so far, but this is the length of the gradient. So length of any vector, by the way, length of any vector, it is simply, the square root of the sum of the squares of the values. So square root of the sum of the square of its values. Like here, there are 2 dimensions. So that means we'll take the square root inside. It will be the sum of the squares. So 2 square plus minus 4 whole square. So 2 square is 4 and 4 square is 16. So this is how, this is why it's coming. So it's the length of the gradient which is
So
required.
the absolute value of f of x is the length of the gradient.
Yes. Yes, it's the length of the gradient. Yes.
So it's
But
not
this is the
included
absolute
in the
value
exam.
of this is not the absolute value of the function, but this is just, you can say, the absolute value of the direction, right? Or not the direction even of the derivative.
Uh-huh. So this kind of a question is not included in the midterm.
Yeah, I mean, if we
I
ask,
mean,
this one is
the
included.
length.
Yeah, this one is not included. So coming in the next week, inshallah, this one.
Uh-huh.
Right? And then I mean, how to determine that this is, for example, a positive semi-definite or not, because this is related to the convex. Because if somehow we are able to prove that this function is or the q is positive semi-definite, then we can say the function is convex. So what we need to do is, the first thing is we just have to take the first row, and the signs are like plus, minus, plus, and then what we do is I kind of ignore the first row and the first column. So I will just get these values. So this is like 10 multiplied by minus like 4 multiplied. Yes. Um, just wait.